Alright, here's the first of my companion videos for the Giancoli book. I'm going to start with chapter 16, and I'll try to give you updates here on the video of which sections I'm talking about. So let's start with sections 1 through 4 and talk about the main things from those sections. The first thing is this idea of electric charge. The classic place you see it drawn is in an atom. So you got electrons that orbit. Okay, that's not quite true, but you have these electrons that orbit a positive nucleus. And so you have a negatively charged and negatively charged electron, and the nucleus is positively charged. And really, I mean, when we talk about something that's neutral, we're not saying there are no charges in it. In fact, even something like a neutron, so let's draw, hello, neutron, you would think, well, this is completely neutral, so what do you mean you're always talking about charges? Well, if you get right down to it, even the humble neutron has, let's see, 2 down quarks and an up quark. We're actually going to skip the chapter where this is shown, so let's just you know, bear with me. The downs have a -1/3 E charge, and the up quarks have a +2/3 E charge. And you add all those up and you get, oh sorry, that's a third. You add all these up and you get 0. So even a neutron, like the quintessentially neutral particle that we talk about, is not electrically neutral if you could look in close enough. Alright, so much for charge. And the other thing that you need to remember is that negative charges will repel, so they'll feel a force that pushes each other apart. Positive charges also repel each other. Okay, so those are the directions of forces. But if you have a positive charge and a negative charge, then they attract. And this you have probably seen before, right? This is kindergarten problem. What I tell you. Alright, I had this Russian professor who used to actually say that. I'm not making it up. Okay. The other main thing to know from this, insulators are materials that have charges that are stuck. So insulators, their charges can't move around freely. Conductors, they have electrons that can move around, and we'll get into the details way later in the course. And the last group of materials we'll talk about are semiconductors, and these are at the heart of a lot of the technological advances that have come in the last 100 years. Semiconductors are awesome because you can control exactly how many of the charges you want to be free to move around, and you can do just beautiful things with them. Alright, that is sections 1 through 4. So let's go on. Sections 5 through 6 of chapter 16. Alright, this one is all about Coulomb's law. Now, we saw that on this previous page. You see that negative charges, well, okay, like charges repel, opposite charges attract. It's a simple rule. Coulomb added a little bit more. He tells you how to find out how long those force vectors are. Remember, a vector has a direction and a magnitude. We now know the direction. All we need to know is the length of the line. Okay, so Coulomb's law gives us that. And we have the force is equal to K, the first charge, the second charge, over the separation distance between 1 and 2, the separation distance squared. So here's our situation. We have Q1, we have Q2, Here is R1, 2, just separates them. And K is a constant. K is equal to 9 times 10 to the 9th Newton meter squared per Coulomb squared. That's important. We'll see that quite a bit over the next few chapters. All right. So this is how to find the length of these force vectors that we already saw when we talked about this. So here are the rules for doing Coulomb's law problems. First of all, draw the direction of the forces. Like, attract, opposite, repel. All right, and then ignore the signs, and that's important. So ignore the signs of the charges while you calculate the magnitude of the forces. All right, that is the main thing with sections 5 and 6. You do need to understand superposition, which just means, I mean, you know this from 105. If you have two forces that act on an object, then you just add up the forces. It's the same thing with these objects that we're talking about. If I add a Q3, then Q1 will feel a force, let's say that it's attracted to Q2. So that's F1, 2. So let's say this is positive, this is negative, and this is also positive. It's going to feel a repulsive force from Q3, and so you draw that like this, F on 1 from 3, force on 1 from 3. And the net force on this is just going to be these two vectors superposed. It means you add them like vectors. And if you need a vector review, Chapter 3 is a good place to look. All right, let's do a new, Okay, let's do the very last of this chapter. That would be sections 7 through 9 of Chapter 16. All right, so this one is not my favorite section in the book, frankly. If we go back to Coulomb's law, it says that the force is K, Q1, Q2 over R squared. Let me draw an analogy. Because this looks so similar to gravitation, let's just put gravitation here so that we can make some comparisons. The force for gravity was this big G, the gravitational constant, times m1 times m2 over r squared. These should look extremely similar. Mass is like charge, G is like K, and then the separation distance is the same. These have exactly the same form. They just have different lengths for the vectors. Okay. So what if you wanted to write this in the same kind of shorthand that we always drew the gravitational force, or almost always? There was one chapter where you may have used this. But if I have, say, a box, and I want you to draw all the forces acting on a box, oh man, this should bring back some post-traumatic stress. But anyway, this is, you would have written this as little m times g, right? And then you would have written another one that was up, and it's the normal force. This is why the box doesn't move as it sits on this table, because the normal force is the same size as the weight. But hold on, this is the gravitational force. So how did I go from this to something that looks so much simpler? Well, the answer is we write it as, okay, here's m1 out here, and then you've got little g would be g times the mass of the Earth that's mass 2, all over the radius of the Earth. That's the separation distance between this, the center of this object, and the center of the Earth, squared. Alright, so this right here must be g. Now, we called this the acceleration due to gravity. I'm going to claim to you that this is what we should call gravitational field. And if you look at the Earth, so here's our Earth. It's got this big M. The gravitational field points inward no matter where you are on the Earth. And it's a handy little shorthand because now you can say, well, if I have some little mass m out here by the center of, or by the surface of the Earth, it's going to feel a force equal to the gravitational field times the mass. It's so much easier than going and looking up these numbers and plugging them in. Well, it's the same way with electrostatic force. So let's just have a look here. What if we said, we just want to redraw this without all of this gobbledygook. We just want a charge times some new thing, and we're willing to call it electric field. That's okay. What would electric field be? This is my favorite way of finding out how to define electric field. Okay, so if you look up here, you pull out one of these charges, call it Q1. It's Q1 times K Q2 all over R squared. So this right here must be E. Alright, so this is nice because if you can find the electric field at any point, kind of like we did for the Earth, you just multiply it by the charge you want to know the force, the charge that is experiencing the force you want to know. Multiply that by the electric field at that point, and if you know the magnitude and direction of electric field, you know the force acting on that charge. So that's the reason, the motivation for coming up with this is that E is easier to write than KQ2 over R squared. Okay, it sounds like a pretty petty reason to do that. And the other advantage is that you can find E for any location in space given some configuration of charges. Say you've got one charge here and one charge here. Actually, I'm going to refer you to example 16.9. There's a video for it in the chapter 16 videos. And there I show you, you can find the electric field at a couple of points. It's nice because once you have the electric field, no matter what the charge is, you can find out what the force on it is. When you're drawing, this is the last thing I'll say. Let's say that you've got a plus 2Q charge, and you have another charge that's minus 3Q. You need to make sure that your field lines, I'll draw them in yellow, that you set a key. Let's say that there are two lines, oh I thought I got yellow, 2 lines per Q. That legend will help you know, okay, this is 2Q, and since I've got 2 lines per Q, I need 4 lines to leave the positive charge. And over here I've got 3 negative charges, 3 negative Qs, and so I need 6 lines to go into this negative 3 over here. So here's 1, here's 2, I've taken care of 1 Q's worth. There are 2 more that need to leave there and end. Okay, and then there are 2 that come from who knows where, but also end on this negative charge. And so if you zoomed out, just picture with me that we've zoomed out to where all you see is the little orange piece and the little red piece. Maybe I'll make it red so that you can picture it with me better. I love that story. Okay, so we've got this. We've zoomed way out to where there are little tiny dots in the distance. And what you would see are 1, 2 lines coming in. See those 2 lines? And so this looks like a -1 charge. If I zoom out far enough, 2 of these negative charges are canceled by the 2 positive charges, and I look like I have just a negative Q here. Does that make sense? Hopefully. I guess I shouldn't ask questions to the microphone. That is all of Chapter 16 in, I don't know how long it took me, 15 minutes. But that should help you. It's not designed to take the place of reading the textbook, but it should help you get through some of the trickier spots.